Hello, everybody. Good morning and good afternoon to everyone. I am Thiago. I'm part of Encora Brazil division team, and I'm very pleased to be your host in this session. This session of today is dimensionality reduction. Before to introduce the speaker, I would like to remind you that you can follow us in your social media appearing on your screen. So do it to be aware of every news, okay? Another important point, this session is part of Global Devweek organized by Encora. And finally, you can use the chat to leave comments, ask questions to speaker, and etc. The speaker will be happy to answer all your questions also using the chat. All right? Well, so our speaker today is Arun. Arun is software engineer working with Encora for more than 8 years. Have worked on back-end applications development for long and have driven architecture and design changes. So let me invite Arun to lead the speech. Welcome, Arun. It's up to you now.
Hi, hello everyone. Um, thanks for a very nice introduction of myself. Um, as was introduced, the topic today is dimensionality reduction. What is dimensionality? What is basically what is a dimension? So in data science parlance, we deal with huge or humongous data, and this could have multiple. For instance, what you see in the pictures here down on the right bottom corner. You see, this is basically a sample data set uh, that's available for free, and it's used for practicing some of those machine learning models. So here you would see that it has say like four, six different columns. In reality, a complex machine learning model uh, would have like if I look into if we talk about some of those deep learning models, so they would have about a trillion or more than a billion parameter sets. And so the one of the main challenges would be, so if you have like huge data sets, where the volume is around um, a billion, so it's one of the things that the challenges that we get into are the complexity in modeling such humongous data set. Um, so that's where. So here, what we are showing here is a simple data set. So what is basically a dimension, right? So dimension is nothing but a column. Okay. So here we see ID as a column, the sepal length, the sepal width, the petal length, petal width in centimeters, and the species. These are various different columns, and these are interchangeably referred to as features or dimension. So in a data set which has large features or dimensions, so that would pose a lot of challenges in coming out with a right model and building this right model. Okay, so I'll just move to the next slide. So, as I was talking about some of those features which could influence the model accuracy, what I have listed, what we see here is a list of factors that can impact or adversely impact the model accuracy. So here we see data quality. Um, so the data quality is very important with the data set. So if we have the data with inconsistent quality, so one of the things that we end up having is the model accuracy uh, on the test data would be far lesser. See, usually the accuracy is around 80-90% or so. So if we have too much of data inconsistency, it could also lead to, as I said, very low model accuracy. And so the data quality could also be um, missing data or the outliers. So, for instance, what is exactly an outlier, right? So, outlier is basically, so we have average of say the petal width or petal length to be around close to 20 centimeters. And if we see data how which is say 80 centimeter, and there's a very high standard deviation here, and anything beyond 50 centimeters, we could treat those data values as outliers. And outliers also would impact the model accuracy. Okay, so the feature selection. So the next one is basically, so here, if we have a humongous set of features or the dimensions within the data set, so next comes how do we pick and choose those features or dimensions which are required for model building. One of the key things here is look for correlation between the features. So when I say correlation, um, there could be few features which are closely related. So there are algorithms which can detect the correlation, and one of the key things that we use in the model building or while before the model building while doing the feature engineering is that we use some of those um, techniques like Kendall and to basically detect the outliers. So the next step is basically feature scaling. So when we do any of those model building, so we need to make sure that the data is scaled. So usually we have varied data. So one feature probably has a centimeter, and other feature within the same data set, it could have data in meters, right? So you need to actually normalize this data. So how do we normalize this data? So one of the ways, this common ways that is followed is to actually use scaling, the standard scaling and the min max scaling. Okay, so without using the scaling techniques, so this could have repercussions on the model accuracy. And the other thing that we usually do while model building is, so we would really select the type of model. So if we are building a model, the data could be, it could be a classification model or it could be a regression model. So for instance, a regression model is where we usually have this, say, we need to predict sales data. So we need to, from the sales data, we need to predict what would be the sales for the next 3 years, right? So that could be kind of a regression problem that we are going to that we need to handle or tackle. And other problem would be typically a classification one where we have a data set and we need to see it's a binary classification, or if it's not binary, it could be multi-class classification as well. Okay, for instance, if you want to detect the cells have cancers, the human or the biological cells, do they have cancer? Is it cancerous? Is it carcinogenic? So if we have the data, so we could predict, yes, the cells are cancerous. No, the cells are not cancerous. So it's a binary classification. So here, so what models we select, it's quite important. The hyperparameter tuning is, at the time of building model, there are numerous parameters that could be tuned. For instance, we have, I would give you some lambda, so where it's applied for regularizing the data. So for regularizing the data, we apply the lambda. The higher the lambda, the higher the penalty that is applied on the data set, and you would see more penalty being applied during the model building. So there is a fine balance that we need to strike to come out with a appropriate value for lambda. Similarly, for instance, there is a learning rate, which would basically is all about how fast the model can converge. So the higher the learning rate, higher the convergence is, and the higher the learning rate, so this could have an impact on the accuracy as well. So again, we need to strike a appropriate balance here to tune these parameters. And the lower the learning rate, so the accuracy and the precision of the model will be higher. Okay. So and the training data size is also another factor that can impact the accuracy. The too small data size definitely will have an impact on the accuracy. So how basically, right? So you could we could end up having underfitting model, which is probably not trained on all types of data. So data size with the right set of classification, we need to include for a classification kind of model. You need to have a right balance of classes within the data set, so that it can learn the unseen data as well. So bias and imbalance are somewhat closely related to the training data set, in the sense, if I'm building a classification model, so if my data has, say, cancerous cells, probably 10% of it, and 90% of it are non-cancerous, so there is a data imbalance here. Right? So I need to do some kind of resampling, apply resampling, or generate more data with probably cancerous cells, and then remodel, uh, apply and build the model on top of this resampled data. I quickly talked about overfitting and underfitting. So overfitting is basically when um, so we have this data set, and it is trained on a complex data set. It's extremely complex data set, and as a result, it has learned something which it's not supposed to learn, and that's something not really required. uh, and that's where the overfitting comes into picture. And we need to have, again, we need to resample and see the data where it's not supposed to learn something it's the model is supposed to learn. So we need to see the data, balance this correctly, so that we avoid the overfitting. So underfitting could be one more challenge. Okay, so if I have a very simplistic data set, um, so it uh, it basically is not trained on complex data set, and as a result, when we encounter a data which is more complex, the model accuracy is very low. So so these are all the different factors where that can influence the accuracy of the model. So we need to see, these are the factors where that are applied while doing the feature engineering on the data set. I'll move to the next slide. So next slide is all about uh, there is a common term that is used, which is curse of dimensionality. So it refers to different challenges and issues that would arise when working with high dimensionality data. And the performance and the efficiency of some of those algorithms would deteriorate if there are too many number of dimensions. See, as I said earlier, so in the deep learning um, parlance, uh, we would end up having features which are several thousands or several billion. So what would so the things that we would end up having, the challenges that we would end up having because of high dimensions, could be the increased sparsity. Increased sparsity And computational complexity. See, we would need a cluster of GPUs, graphical processing unit, to run this model, and the model building and the model training itself would take several hours to few days, and it could take a run up to a week as well, for a high dimensional data set. And so this would also, as I said in the earlier slide, there is a very good chance that we would run into the overfitting if we have too many features, and there is a possibility that it could get overtrained, and this would lead to overfitting as well. So we probably are training the model on a data set where there are some sections of the data which are definitely not required for prediction. So such things we need to eliminate and balance the data. And so other important challenge is that the visualization challenge. So when we want to visualize the data which is having too many features or very high dimension, so it poses a big challenge to visualize this data. Um, so let me move on to the next slide here. So this slide basically talks about various techniques that are applied in the data science industry on how to reduce the dimensions. So the first thing what we see here is the PCA, the principal component analysis. So this is a technique where it identifies the high variance and the high quality. So the high variance in the data um, captures the high quality as well. So retaining the data which has a higher variance would also mean that the quality of the data is good. So this would identify such data and categorize those as principal components. And once it identifies these principal components, which are far fewer, say if we have like thousands of dimensions, so we can set, okay, I am interested in say this many components, say probably 30 components out of several hundreds. And then we can apply run the PCA on this, and so we should be able to use the reduced um, reduced feature set for further model building. Okay. So linear discriminant analysis is the next technique applied for reducing the dimensions in the data set. So what this does is it basically this is it uses, see, in case the data set is an n-dimensional data set, and so what this does is it transforms the data set into two or three-dimensional data, while retaining the quality of the data. And then it basically tries to minimize the number of features or the dimensions by transforming the n-dimensional space data into two to three-dimensional space data. So there is this next technique, which is basically stochastic neighbor embedding, distributed stochastic neighbor embedding. This basically is a nonlinear dimensionality reduction algorithm. So where this will identify the groups or clusters and patterns in the high dimensional data, and then it will segregate the clusters and the patterns, and then thereby reducing the number of dimensions in the data set. So isomap is another technique for dimensionality reduction. So this is basically a nonlinear dimensionality reduction technique that again similar to linear discriminant analysis. It constructs a low dimension embedding, and it basically uses the distance between the data points. So that's one of the key things here. And then it captures the intrinsic structures of intrinsic structure of the data by using the data points, by using the distance between the data points. Okay, so these are other couple of techniques that I have. There are a whole lot of different techniques, but I have minimized it to probably the six different techniques for reducing dimensionality. So this one in this slide, the first one is about the recursive feature elimination. So what this does is it uses the data set, so then computes the scores, the feature scores or the dimension scores, which are basically called as importance scores or the coefficients for each of the features. And then once this is done, so the technique it applies to reduce the dimension is with the features with the least scores, least important scores are eliminated. And so the same thing can be recursively applied. So now after the after the initial data set, it computes the important scores, and the least the features who have the least scores are eliminated, and it is applied recursively. Then we have a reduced dimension data set, and the similar technique is again applied, and that's the reason why it's called as recursive forward elimination. So the next technique is basically a variance thresholding. Here, the variance of each of the features are calculated or can be computed. That's very easy to compute a variance of every feature. And then any feature which has variance of say point 0.2, 0.2, it can be eliminated. So we can put a threshold. The threshold here means, okay, so I would probably draw a line saying that, okay, any feature with variance 0.2 or less, I would want to eliminate this. So this is another technique, the variance thresholding, that can be applied um, to actually reduce the number of dimensions. Okay. So I had this many slides. Now, what I would like to do is I would like to go over some of the problem solving uh, notebook, the notebooks where some of those techniques are being applied to reduce the dimensionality. Okay, so here okay, so this is one of the this is the Google Colab notebook. So what I'm showing here is a Python program where I'm using the standard data set, which is basically the uh, plants related data set, iris data set, where it has this many features, and I mean features is 4 number of columns, and the rows are 150. So here we apply the scaling techniques, standard scaling on the data, and here we do the PCA, principal component analysis, so where I select 3 components, and I also use the SNE, which is the stochastic neighbor embedding, again selecting 2 components. So, and then finally I try to plot the graph here. Okay, so this particular has 2 groups of data set. Okay, if you see here the one with one set of color, the other one in different color. So this is one of the techniques where this can be applied for reducing high dimension data. So next one, okay, so this I have a sample here where I want to showcase the variance thresholding, what we just talked about in the slide. This can be applied on a standard data set. So there is a standard data set, what we see here in the notebook, which is the cancer-related data set, the breast cancer-related data set. So when I print this, so it has, see, I want to just see what's the number of features and what's the number of rows. So it has 569 rows and 30 columns, which is basically 30 dimensions. What I'm trying to do here is I apply a threshold of 0 to here. So some these are the import has this library for using the variance threshold, and then finally I fit this on the data set, and then I apply this one, and then finally once after applying this, I see only these many features, so which are say around 11, 11 features. I reduced from 30 features. So what we see here is 30. I reduced it to a list of 11 by applying the variance threshold technique. Okay, so the next one I would like to showcase here is the recursive forward elimination we talked about in the slides. So here again, this is a separate notebook, and we use the standard the breast cancer data set, and then we apply the scaling. We talked about this. There are min-max scalar and then the standard scalar, so that we have, if we have data, say one is in centimeters, is in meters, one is in feet. I would want to normalize this data. So now the standard normalization technique is all these techniques are standard scaling and then the minimize scaling. We use the standard scaling here and apply this on the data set. And what's the model that we are selecting here? The logistic regression is the model that we are selecting here. And then we want, say, from this 30 feature or dimension data, so we want to minimize this to 15 features data set. This is using the recursive feature elimination dimensionality reduction technique. So I apply that, and finally, I print what are the selected ones. So as discussed in the slides, so it would internally compute the scores, the importance scores or the coefficients for each of these features. The ones of the features or the dimensions that have the least coefficient of the score would be eliminated. So and then final set of features is what we see here. Yeah, I think that's all I had for the presentation on dimensionality reduction. Thank you so much.
Okay. Thanks, Arun. It was a really great session. Thanks for our shared knowledge. Thanks to all of your audience for your time and messages. I hope you've enjoyed this talk with Arun. Remember to return to official website for the next session. I hope to see you all soon. Bye bye.
Thank you. Thanks.